Okay, first I want to thank the organizer giving me this chance to have the talk here. Actually, my advisor, Professor Tim Malkoff, is running a seminar about this compressed sensing in my department. Hopefully, after this talk, you will feel interested in this topic. So actually, compressed sensing have a very clear application background. Consider our digital camera we are using today, the CCD. That means the sensor of the camera with higher and higher resolution that increased from 1 MP to 10 MP in just a few years. But usually we threw away most of the data we get via several popular compression algorithms, for example, JPEG 2000, because the original data is too large for storage or transmission. And sometimes such high definition is not necessary for our need. And in other applications, including imaging system, like medical scanner or radar, increasing resolution is very expensive. So our question is, can we avoid this high sampling rate? Compressed sensing provides a new idea to compress a signal in the acquisition stage. Okay. So first, what is sparse signal? Okay. Consider a one-dimensional finite length and a discrete time signal x. So we can view x as a n by m column vector in Rn. So if our data is image or higher dimensional data, we can vectorize it into a long one-dimensional vector. We define the L0 norm of x to be the number of non-zero components of x. So if the also we call this to be the sparsity of x. If sparsity of x equals k, where k is much less than n, and we call this x a sparse signal. Why is this sparse case interesting? So if f in Rn is a general signal, and we have a n by n matrix B represents a dictionary or base of Rn, assume B equals f equals B multiply x. So x here represents the coefficients of the linear combination. For many f, if B is nice, for example, it is trigonometric system or wavelet base, most of the components of x have small amplitude. We can just set those neglectable coefficients to be 0 to have a k-sparse signal x hat. So this f hat equals b multiply x hat. This gives us the proximal of this f. And usually the relative error of this way is small. For k is much less than n. Okay. So I show you the graph here. So this is our original data. It is a 1 megapixel image, and if we only pick the 25K biggest wavelet coefficient, we can have this good approximation. Of course, we lose some detail here, but anyway, we can consider this as good approximation. So in the compressed sensing, we do the work like this. Given a vector x in Rn, and usually this n is very large. Instead of sampling x directly, we ask m questions in the form of inner product. So every time you have a v, you take the So every time you have a v, you take the inner product, and you have your answer as a measurement. Okay, so we can ask m questions. So we write the problem as this way. The measurements y equals phi multiply x, where this phi is a m by n sampling matrix. So with this graph, it would be clear. So the first row, it is your first question. Okay, you have x here. You only have you only have a small number of non-zero coefficients. Okay, you take inner product. You save your answer in the first position in y, and because you can ask m questions, that's why you have m rows in phi. Okay. And this phi, sometimes we call it to be the encoding matrix. We want to solve for x from phi and y. Okay, y here equals phi multiply x. For general x, no way we can solve this ill-posed problem. But if x is sparse, we can. So how to ask smartly? That means, what does rho looks like in phi? Okay, and how many questions are necessary? That means, what's the number for m? It is kind of a little surprised. It is more important than the columns than the rows. Okay. If phi has RIP, which is short for restricted isometry property introduced by Kenneth and Tao of order k, then there exists delta such that the ratio here has lower bound and upper bound of 1 minus delta and 1 plus delta. For all k sparse signal x, define delta k to be the smallest delta satisfies above inequalities. So from here we can see, because we have much more columns than rows, so no way this phi can be orthogonal. But it is not far from orthogonal. It turns out if phi has RIP of big order k, and with small parameter delta k, this encoding matrix is good. So how to construct phi with RIP? We have deterministic approach, but we are not satisfied with k, with order k in this case. So usually you employ the random construction. This can provide bigger k, but with high probability. For example, we can draw the elements of phi from a zero mean Gaussian with 1 over m distribution variance, or we can use random Bernoulli with positive and negative carry the same probability. Okay. Assume this m here is fixed. From above construction, this order k here can equals capital O m divided by log m over n over m. Okay, and after we have the y, and how can we solve for our x? We can use the L1 minimization. Sometimes we call it basis pursuit. This way works very well. We have the following theorem, and we can solve this problem by linear programming. The theorem is given by Kenneth and Tao. If x is in Rn, it is a k-sparse, and phi has RIP of order 3k with this 3 parameter delta k plus delta 2k plus delta 3k. The sum is less than 1, then x is a unique solution for the L1 minimization. Okay. We search over all x prime such that phi multiply x prime equals y, and we find the L1 minimizer. If we have this condition, the L1 minimizer is exactly the original signal x. And we come to the greedy point, and we have some greedy algorithms. One of them is called subspace pursuit. How can we do this? First, we have some preliminaries, and this I is a subset of the set of all indices from 1 to n, and this phi I is, we pick the indices from this subset from the set of I, and we only pick those columns, and that gives us a submatrix of phi. Okay. The projection of y onto this matrix, it is defined as phi I multiplied by phi dagger, which is the pseudo inverse of phi I multiplied by y. So actually, we make the projection of y onto this phi span of phi I. Okay. And the residue here is the y minus the projection. First, we do this initialization. We define this t hat to be the k indices corresponding to the largest magnitude of phi transpose multiplies y. So actually, we do the work like this. We have our y, and we do inner product with every column. Okay, and we find out which k column give us the biggest inner product. And that set of indices give this t hat. Okay. And then we make projection onto this phi t hat, and y minus this projection give us the residue here, yr. And for iterations, we check first whether this yr equals 0. If this gives us 0, we quit our iterations. Otherwise, we go on, and we find this set t prime. T prime equals t hat union the k indices corresponding to the largest magnitude of phi transpose multiply yr. Okay. So YR is the residue we get from last step. We take this residue and we do inner product with every column. And we pick the k biggest indices. And this union gives us T prime. And we make a projection onto this phi T hat dagger. Okay? We check the coefficients of the projection. And we pick the k of them, biggest k of them. And then we do projection, we do new projection on this T tilde. And we find the new residue, YR tilde. And when can we stop? If the YR tilde, if the norm of the residue increase, we quit. Otherwise, we go on. We define this T hat to be T tilde and YR equals YR tilde and go on. And when we stop, we have some set to be T hat. We make projection. We find the coefficients of the combination that give us X hat T hat. If the indices is not in this T hat, we just set the element to be 0. Okay. So maybe I can explain with this graph here. So first we have this T hat. That means we pick the k biggest. And then we calculate the residue. And we do inner product again. And we pick another k biggest. But maybe some of these indices from this T hat is bad. And how can we kick this out? Among these 2k, we pick another k biggest. Okay. So we do the work like this. And actually, it works very well. We have this Cerium by Dai and Milinkovic. If X is in Rn, be k sparse, and Y is given as phi multiply X. If phi satisfies RIP with delta 3k less than 0.06, the SP algorithm guarantees to recover X exactly from a finite number of iterations. And how many iterations is sufficient? Actually, the number of iterations less than or equal 1.5k divided by negative log ck. Ck is a constant depend on delta 3k. And actually, I can improve this a little bit. If this delta 3k is less than 0.46, we only need the number of iterations to be less than or equal k. And we have an idea to weaken this subspace pursuit algorithm. So is this stable with computation errors? So when we pick the first, after we take the inner product, we want to pick the biggest one. Okay. Instead of pick the biggest one, we have a strip. It is a value plus epsilon and minus epsilon. And actually, we can pick anyone in the strip. Okay. And next step, instead of pick the second biggest one, we can pick anyone in the strip, and so on. And we want to find out that this algorithm is stable if this, and what's the relationship between the stability and this epsilon. And actually, I'm still working on this problem. Okay. Thank you. Yeah. And what if you don't know? What will you do? So actually, we can try the sparsity from small to big. We can make static. First try 2, and then 4 and 8. We have this one way, and there's another way called Bayesian compress sensing. They can find out the sparsity even if you don't know it, but they use different techniques. Thank you.